hear there's mojitos to be had afterwards for all of the graduating students. So for those of you who may be coming just to this one, there were 4 HCI dissertation defenses this week. And Ron told me he's going to give the best one. Ron was my very first student at Stanford. He emailed me even before I started and said, hey, I hear you're teaching a graduate HCI class. I'd really like to TA for you this fall. And so this was a brand new class for me, and having Ron was in essence the expert. I was the newbie, and he'd been around here for several years at this point. So Ron really helped me get started as a teacher here. Ron was also my very first student to do research with. When I got here, Andreas and Hector and some of the folks in the digital libraries group said, we're working with field biologists. Do you have any interest? And I was like, I just got here. Sure, that sounds fun. And so Ron and I started hanging out with some field biologists, as he'll tell you. And what was amazing is it's working in a really different domain. It can be hard to get started, and you kind of poke around and try a bunch of different things. And then one day, Ron just came in, and he was off and running, and he's never stopped since. And I think my favorite moment in when we first started working together is he came in one day in the winter, and it was cold and rainy, and I bike in, and so I think I was wet, and it was cold and rainy. And Ron goes, do you know what? Some of the biologists are going down to the rainforest in Mexico over spring break. I think it's really important for my research that I go down to the rainforest over spring break. And it's so, great, sounds good to me. And so Ron was on a plane with a dozen laptops and a bunch of technology that he somehow pulled out of thin air right in time. It was really remarkable. The other thing that I've been really impressed with Ron's work is that he spanned a lot of different departments. We're all computer scientists, we're comfortable engineering, and maybe we venture out a little bit, we say hi to other kinds of engineers. And what Ron's done is he's pulled together, if you look at Ron's committee, includes Roy P. from education, there's several biologists in the audience, we've spanned, we've got, he'll tell you who's using his system now, and it really spans just the language barrier between all of those fields. Being able to broker that is really impressive to me. So, Ron.
Thanks, Scott. This afternoon, we're going to discuss paper plus digital interactions, which are applications that integrate our use of computers with the very familiar tools of pen and paper. So you might be asking, why am I interested in paper in the first place? Well, it's because that even in the digital age, paper tools are ingrained in every facet of our work and play. We use Post-its to capture brainstorm results, to remind ourselves of what tasks we have to do. We might create origami to give to our best friends. In the book, The Myth of the Paperless Office, Abigail Sellon and Richard Harper detail the affordances of paper. And they say that these affordances are what lead to paper's continued use. Paper's readable, it's graspable, it's flexible, it's robust. Here's a picture of the Dead Sea Scroll, a part of it. It's lasted 2,000 years, and my floppy disks from the 1980s don't even work in my laptop anymore. Paper is easy to annotate, and you can view it side by side. However, the content on paper is not easily searchable, and we can't actually share it very easily with remote collaborators. Thus, if we create software that can integrate our use of paper with computers, we might be able to benefit from the robustness, flexibility, and mobility of paper with the searching, storage, and sharing that we depend on every day. There are a number of ways that you might augment paper with computation. The current best solution is the Enoto digital pen. Here's one of these pens. The way it works is that there's a camera inside the pen pointed at the tip, and it tracks a tiny dot pattern that's pre-printed onto that page. This dot pattern encodes a location X and Y in the notebook. And as you write, it stores a vector graphics representation of your handwriting. And every single stroke, it actually stores the X and Y, the timestamp, and also the force of every stroke. If you want to create software To interface with this pen, you can actually use Onodo's provided software development kit. The platform models digital ink on pages of notes. The program can actually retrieve this ink every time a user plugs in his pen to his PC through a USB port, much like you might plug in a PDA or a cell phone these days. Francois Guimbertier's pad system extends that model. It overlays the ink back onto the original PDF. However, neither of these systems can handle real-time events, even though the pen can talk to your computer over Bluetooth wireless. For an example of a real-time event, we might make a gesture-based application, maybe one that can control our PowerPoint slides. So if we go mark left, it might go back one slide if it actually would work. And it did. If you go right, it might go to the next slide. Signer's iPaper system can actually interface with this pen in real time. However, it actually models pen interactions as a database query. When a user taps on a location on this page, the coordinates are sent to the remote database. It responds with some media, such as a photograph or a sound file. And this approach, while flexible, is a little bit heavyweight for most applications. It actually introduces extra latency because of the network requests. So our goal then is to create a better toolkit. Ideally, this toolkit will be familiar to help existing programmers create these new types of applications. It'll handle real-time event handling, real-time events, beyond simple pen taps. It should be lightweight. It shouldn't require any extra infrastructure, and general enough to subsume and replicate those prior approaches. So therefore, we seek to enable paper and digital applications through a toolkit and software architecture, allowing programmers to rapidly and flexibly create these new types of applications. This goal brings up a couple of research questions. First, what types of applications do we want to create? Which ones are useful? Who will use them? Second, how do we build and debug these applications? How do we evaluate them? And how do we evaluate the toolkit that allows us to build these applications? The main thesis of this work is that to create paper and digital applications, we can treat paper as an input surface in a larger ensemble of computing devices. We can extend the event-based model of graphical interfaces while accounting for the unique aspects of paper. And this will provide developers a smooth transition into this new style of programming. So let's build the toolkit. This research offers three main contributions. First, we contribute an in-depth field study of a user community, which helps us determine requirements for this augmented paper toolkit. Second, I introduce novel interactions, including a smart paper notebook and large printed posters and maps. These applications actually inform the design of the system. Finally, the work presents a platform for building applications. We describe the architecture, the evaluation, and novel techniques for developing and debugging. And each of these contributions will be fleshed out in the rest of my talk. So next, I'm going to talk about the field study. I will then describe the two systems, ButterflyNet and GigaPrints. I will describe Paper Toolkit in depth, and then talk about how we have evaluated it and how we have responded to the results of that evaluation. Before we go and start building interfaces and toolkits, for that matter, we need to know who will use these paper and digital applications. When and why will they use them? To answer these questions, we can actually look at one extreme user group. In my case, I studied field biologists, as Scott mentioned. When I started this work, I interviewed 13 biologists here at Stanford, at Jasper Ridge, and the Cal Academy of Sciences. I quickly learned that paper's centrality to biology's work practices. For example, biologists depend on paper's robustness for preservation of data. Over there on the right is a picture I took of Tracy Storer's notes from 1925. It's actually locked away in the archives in the Cal Academy. This inhibits sharing. Biologists capture many types of notes. I'm just going to show you two of them. Tabular data on the left, prose describing procedures, lists, and I've boxed in red there actually a link to a digital resource. That's a name of a spreadsheet file that the biologist has edited recently. Beyond the structured interviews, I also took a 20-week course to train as a docent and researcher at Jasper Ridge. I've collaborated with researchers. In total, this comprises 400 hours of observing, working alongside, and actually living with, for that week, biologists. Let me tell you about two of these biologists, Brandon and Sarah. Brandon spends 6 months out of every year in Costa Rica studying bees. He and his teammates wake up every morning at 5 a.m. to go to 6 field sites. They capture bees, return to their laboratory where they spend the night identifying them, measuring them, entering data onto their data sheets. Once they're done, they collect these sheets together and transcribe them into an Excel spreadsheet. He and his teammates demonstrate that biologists capture heterogeneous media, specimens, notes, and they can use support for structuring this type of data, transcribing this information. Compared with Brandon, Sarah has a relatively easier field season. She works at a high-tech biological preserve near her university. She drives out to her sites on electric carts. She walks around the GPS loggers, audio recorders. But even then, she writes down her measurements on 4-foot-wide paper maps that she folds and takes out to the field, only to transcribe and correlate this data later with her mapping software. So Brandon and Sarah are representative of the types of users I want to target. They're mobile, they depend on paper, but they're not afraid of technology. And since meeting all these biologists, I've been able to create some personas to describe the different requirements that we want to target. Amanda captures photographs, video, and handwritten notes. She needs efficient search and retrieval software when she works in the lab. Bruce captures audio and data entries of the birds he studies. He needs to be able to transcribe all of this data and associate them with the right bird calls. Carol works with biologists both here at Stanford and in the Rocky Mountains, so she could benefit from support locally, support for collaboration locally and remotely. And finally, Darren works with GPS. He prints out high-resolution maps, and he would like to use them in the field for field data capture and retrieval. From what we've seen here, these paper tools are central, but they have limitations. But if we can augment them, we can actually enhance all of these types of tasks. So we've studied field biologists in depth, but we can actually apply some of these findings to other disciplines. Who else can benefit from these applications? Well, engineers, designers, artists, lawyers, students. Right? By studying one group in depth, we can actually go step back and apply all of our findings to these other types of disciplines. So let's begin to think about what types of applications we might want to create using this toolkit. One design concern is the form factor, how the interface will be used. Is it a small notebook? Is it a large paper map? Can I manipulate freeform, or is it stuck on a wall or on a table? Can the field biologist take this interface outdoors, or is it supposed to be used inside? Additionally, how will the user work with the system? Who provides the content? Does the user write notes, generate most of the content, or does the system print out all the maps and data sheets? And also, does the user use it by himself, or does he work in a team like Brandon's and Sarah's? So now we've seen how users can benefit from augmented paper. I'd like to take a look at 2 applications we built early on in the process. By building applications from scratch, we can actually quickly learn what we need and what would be beneficial for our toolkit. Since I was studying biologists at that time, I first tried to augment data transcription through a better spreadsheet interface. To test whether this prototype worked, I deployed 10 digital pens, notebooks, and laptops to a research class taught in Los Tuxtlas in the rainforest down in Mexico. There I supported and observed 4 collaborative field experiments, including line transects, where biologists actually walk along a predetermined path to take measurements of specimens that they find. And I tested my basic transcription aid. So this is what the basic transcription aid looked like. The biologist works out in the field, captures her notes along this transect. Back in the lab, she can synchronize her pen with her PC, view those digitized notes in the browser, and then select and send digital ink to the spreadsheet. So here the biologist can select some digital ink, say, send it to the spreadsheet, and as she types, a line actually helps her keep track of which line she is entering without having to look back down at the paper page. That's a very simple interaction. From this trial, we found that augmented field tools showed promise. We also learned what we needed for our toolkit. Beyond ink capture and access, we should support handwriting recognition. It'd be nice if we could actually recognize some of those numbers with biologists. And we should support sharing and collaboration, because many biologists divide up their work into teams and share the effort of taking notes out in the field and also transcribing those notes. I extended the augmented biology tool into our first application, ButterflyNet. ButterflyNet supports the existing practice of capturing heterogeneous data in the field, including photographs, map data, sensor logs, GPS information, and handwritten notes. In this discussion, I'm just going to concentrate on photographs and handwritten notes. To use ButterflyNet, a biologist uses his pen and notebook and camera just like he does today. He can write some observations, for example, at 4:43 p.m. He can take a photograph, maybe a minute later. Behind the scenes, ButterflyNet associates these two pieces of media by their timestamps. When he goes back to the lab to upload his notes and his photographs, ButterflyNet presents a browser. He can page through his digital notes, and as he is flipping the notes on the left, the context panel on the right updates automatically to display the most related photos in time. So those photos right there are photos that are taken between 2:49 and 4:16 p.m. But you might want to manually associate a photograph into a page of your notes. To do this, a biologist uses a camera. In this case, it's a prototype of a smart camera, to take a picture or browse to a picture that you've taken before. The biologist can then draw a gesture into her notes. This photograph is associated with that location in the notebook. Back in the lab, in the digital browser, the photograph is rendered right into the brackets that you drew. ButterflyNet also includes a multimedia spreadsheet that helps transcribe data, as we saw earlier in this talk. So does this work? To find out whether these interactions would be useful for biologists, I tested ButterflyNet with 14 biologists in the field and lab study. I tested the field tools, including automatic and manual association, and the lab tools, including the browser and the spreadsheet. This task was actually modeled after the line transects that I saw in Las Tuxtlas. So we had people go along a line, capture data, and transcribe it into their spreadsheet. So how do we gauge success for this ButterflyNet tool? We wanted to look at two things. First, would biologists feel that the tool matched their expectations of use? Do they feel that it slowed them down in the field? Because field time is very precious. And would they use it? Additionally, this study helps us to identify places in the paper and digital design space that this toolkit has to support when we actually start creating applications. So let's look at some of the questionnaire results. The automatic capture and access didn't speed up or slow down. Right, this is self-report data on a 7-point scale with 14 participants. And biologists felt that it didn't speed up or slow down their practice, which is great. It's basically the same. They found it useful and that they would integrate it into their work. The manual correlation, however, slowed down field capture slightly. It was useful in general, but not all of the biologists found that they would use it or could use it, because in this case we only use photographs, and not all biologists work with photographs. The lab tools helped retrieval and transcription. Most biologists said they would use the spreadsheet. Now, ButterflyNet has since been field tested with biologists at Jasper Ridge and Stanford, scientists, anthropologists, and computer scientists at Intel, researchers at NASA, and also 2 other instances of the Los Tuxtlas class. So what did ButterflyNet tell us about this design space? Well, first we introduced a new design parameter to handle how the user provides the input, either informally through drawings or handwriting, or more strictly through taps or gestures. Additionally, we introduced a category for application output, what the computer does. Digital graphics might be overlaid on top of the paper or presented nearby in a co-located fashion. Finally, feedback can come out through audio or visual or force feedback, haptics. So let's see how ButterflyNet fits into this design space. First, 2 of these axes are actually set by the task we want to support. ButterflyNet supports indoors transcription and outdoors capture, and it's meant for a single user. It's a small and freeform notebook. The user generates most of the data through informal inking. It presents output through co-located on a nearby screen or on a handheld. Synchronous and asynchronous interaction. So it can detect your gestures out in the field or process your notes after the fact. And finally, it provides audio feedback for those gestures and visual feedback in the lab. However, you see we've missed a couple of sections here that we haven't explored yet. Large interfaces, interfaces that support collaboration with many, many users. How does ButterflyNet relate to previous work? With help from the design space, I'll pick out a few salient details of these 3 systems. Pierre Wellner's digital desk, Stifelman's audio notebook, Mackay's A-book. Pierre Wellner's digital desk used a camera and projector to actually integrate paper on a desk with digital graphics, and it was meant for indoors use, and it was large. ButterflyNet instead supports mobility through its portability, the portable notebook. Stifelman's audio notebook allows a user to index audio from recorded lectures. ButterflyNet applies the same technique to multiple types of media. Mackay's A-book allows a lab biologist to add links from notebooks to media using a PDA. ButterflyNet goes beyond the tap interactions with the browser gestures. So at this point, we've seen how we can benefit the mobile scientist, but we haven't looked at those collaborative applications, those activities. How can we support collaboration? So collaboration, 2 to 4, maybe more people. Co-located, I've seen scientists work around tables, around walls in a room, or they work remotely, or video conference, or instant messaging. So what impact does collaborative work have on our toolkit's design? So let's take a look at some collaborative interfaces you might be aware of. On the left, you see Microsoft's Surface table. This is basically from a class of devices that we call digital tables. Multiple users can touch and manipulate photographs on this table. On the right, you might recognize Tom Cruise in Minority Report. He's working on a really large wall display that recognizes his gestures. Multiple people can view imagery on this display. However, these interfaces aren't very portable. You can't actually take a Microsoft Surface out into the field of view. Let me show you some big interfaces that are actually portable. So here are some photographs I took out in the field of biologists using large maps to instruct groups of new docents or researchers. Inspired by this, we created GigaPrints. GigaPrints is a system that augments large paper prints with interactivity. To do this, we actually have to make the interfaces really big. Right? We use a 44-inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right, 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured on the right. 44 inch Epson inkjet printer, pictured I overlay dot pattern on top of imagery so that the pen can actually detect where you're tapping and communicate with a computer in real time. And I've created many types of GigaPrints. I'm just going to show you a few of them and how it explores the design space. For example, this is a photo wall for designers. The designer can tap on a photograph and send it to his mobile phone. Here, we've created a monitoring tool to help people in a computer lab monitor the health of the computers. For example, in the future world, we might have printers embedded in our wall that prints sheets of paper maybe once a week, once a day. And we might have a projected display that displays real-time graphics on top of this interface. And this interface can display high-resolution charts to describe how the computers are working in our lab, 600,000 data points in our case, and provide interactivity through these buttons. So these gray areas have dot pattern on them. So we can tap on this area and say, we're selecting this computer to interact with. One or more users can interact with this big print and query a database to figure out which computers might have been acting funny recently or possibly been hacked. So let's take a look at how this works in real life. A projector actually can display live data. A user can tap on a computer to say, give me all the flows talking to Roberto and to Google, and possibly through Europe. So this will actually show you the results of that query in real time. So we'd like to see if these interactions can support collaboration, yet provide a little bit or enough of mobility. We'd also like to see which parts of the design space are supporting. To do this, I evaluated 3 of my GigaPrints, which supported retrieval and drawing interactions. I brought in 2 users per session for 12 total users. And here are the 3 tasks. In the first task, 2 users played a game of finding photographs. Photos were called out by the computer, and a competitor had to tap on a picture to score points. In the second task, we tested a system that supports video conferencing. Anything drawn on your sheet of paper is actually transported immediately to the other end. Finally, we tested a map that you can actually bring out into the field to retrieve audio annotations. So the user taps on an area and listens to feedback through a Bluetooth audio earpiece. Once again, we collected some questionnaire data from these studies, self-report data on a scale of 1 through 7, and here are 2 of the top-rated questions and the lowest-rated one. GigaPrints helps users visually locate content because they can print lots of content to see more at the same time. And it supports collaboration with colleagues. However, the users didn't find that having multiple pens provided great value at that time. Looking at these in total, we see we're actually missing this end over here of extremely large interfaces, and potentially interfaces that support many, many users. So I went and tried to fill that gap. I created a 14-foot interactive timeline that multiple users can work around using digital pens and mobile devices. What you can do is you can actually walk up to this timeline, tap on parts of the timeline and say, oh, I vote up or down on these issues, or I can add comments and send these up to the web. I can lead discussions. I can retrieve source material, send an article from Nature onto my mobile phone. So here are a few key lessons we learned from our experience in building Butterfly Net and GigaPrints from scratch. First, the Inodo abstraction of ink on pages can't model real-time events that we're working with. We want real-time feedback. Additionally, breaking up the code that supports real-time gesture recognition, so we have this bracket gesture, and the code that does the batched processing of the ink when you plug in your pen, actually leads to code that's very difficult to maintain because you have code on many different computers. From GigaPrints, I learned how we can create interactions by overlaying this dot pattern on top of the imagery, and presenting feedback through nearby computer displays or on mobile devices. At this point, we've covered ButterflyNet and GigaPrints, and now I will detail the design and the decisions that we made when creating Paper Toolkit. So I created Paper Toolkit to support the types of interactions that we built from scratch in ButterflyNet and GigaPrints. The idea is that we should help other developers create these applications much more quickly than I was able to. For example, it took us half a year with a bunch of graduate students to create ButterflyNet, and a week or two for each of the GigaPrints. So it'd be great if developers can create these things and explore these interactions without PhDs in computer science. To determine the success of this toolkit, it should support a large variety of applications. It should minimize the expertise required to build these applications. And for those experts, we shouldn't restrain them from exploring parts of the design space. So they should be able to create novel research interactions. So at this point, I want to discuss how Paper Toolkit helps developers. I have to show you this graph that depicts the learning curve of any programming environment. It's inspired by Brad Myers' work. This graph plots the sophistication of an application, how interesting a computer application you can create, versus the required expertise that you need. For example, with Java, the curve looks a little bit like this. A Hello World application requires some expertise. You have to be a programmer. At some point, you want to create a graphical interface. You need to learn Swing. And when you want to create a 3D application, you have to learn OpenGL. So you have to learn a lot more. Flash has a slightly different learning curve. It's very easy to create graphical applications. However, at some point, you want to add behaviors. So you have to learn how to program action scripts. So you're essentially programming once again. And when you create 3D applications in Flash, you have to learn about perspective transformations and texturing. So you're back at OpenGL. The ideal programming environment should look something like this. A shallow slope to the right. I'm going to define two terms, threshold. This is the basic amount of expertise you need, and also the ceiling, how far you can go using this toolkit, how interesting an application you can actually create. And our key design insight or decision here was that we should first present a familiar programming model to help developers rapidly acquaint themselves to the toolkit. Afterward, we can provide novel techniques that improve upon that model to help make programs more efficient or less error-prone. So thus, the initial curve for Paper Toolkit is going to approximate Java's curve. To build a foundation, to build this familiar way of programming for existing graphical interface programmers, we're going to leverage the ideas in GUI applications. So in a graphical application, you normally have a frame, so a container. You might add a component to it, in this case a button, and you add behaviors, a listener to that button. So every time a user clicks on that button, some code is run. To turn this into a paper application, I'm going to replace that container with a sheet of paper. I'm going to replace the component with a region, and that listener with a handler. And I'm going to replace the mouse with a pen. So essentially, this is very much like a graphical application. Here's a simple program, which should look a little bit familiar to any of you who program in Swing and Java. The developer can create an application with an 8.5 by 11 sheet of paper and add a single region to it. So it might be a button. So he adds a handler, which detects a pen tap and prints out a message, pen tap. So the developer then prints out and tests his sheet. As he writes, the Paper Toolkit system reads the pen coordinates from one or more pens, sends it into the runtime, which converts these raw coordinates into the correct region. You'll find the region that contains those coordinates, or that handles those coordinates, converts it to relative coordinates, notifies the handlers attached to that region, and then runs the code. So in this case, the code might display graphical output onto the screen. The toolkit includes the basic handlers for the most common paper functions. For example, it might have tapping, inking, strokes, marking gestures, handwriting. So we've seen how paper applications can be very similar to graphical applications, but how are they different? So there's two key differences. First, the user might not desire immediate feedback. In ButterflyNet, the user actually just goes out with a pen, works all day with no computer feedback at all, comes back to the computer and plugs it in. So we call this a batched interaction. Second, paper does not provide real-time updates. It's a print once type of deal. You can't actually display pretty graphics in real time. So to handle that first case, we provide a new pen sync abstraction, which subsumes that Anoto approach, allows you to grab all the ink from a sink. Additionally, we read in batch pen data, and we actually dispatch events by reading in the batch pen data. To handle the second case of not being able to display real-time graphics, we support output to remote devices. So instead of printing out pen tap over there on line 9, we might add a remote device using this device API. Tell the remote device, a handheld, to display this message, pen tap. Or we might ask it to download a photograph, such as in the photo wall that you saw earlier. So in this case, the device API abstracts network communications. It actually, any call to open URL actually creates an action object, which is serialized, sent across the network to the other handheld, which unpackages the object, calls invoke on the action, which will then download the photograph in a mobile code approach. There are other slight differences. In a paper UI, you need to generate background graphics. We thus allow the user to use any tool that can export a PDF. In this case, I'm actually editing the 14-foot timeline right now in Adobe Illustrator, so it's an existing tool. On the right, we use our GUI builder to augment the PDF. We read it in, and then we can place, add new regions, and name them. And the builder generates stubs that I can fill in with Java code. To support collaboration, we allow the developer to request the pen ID from the event object. For example, in the Twister game, we have pens 0 and 1, pens 2 and 3, or we can retrieve them by name. Finally, modern toolkits should be web aware. We support integration with web applications by exporting digital ink to XML and images. And also, I provide a Flash API for integrating digital ink with Flash GUIs. This is nice because it makes the toolkit more accessible to existing Flash developers, web developers, even though the core of the toolkit is built in Java. Paper Toolkit's an open source project comprising 280 implemented classes, but the main abstractions that the developer sees can be broken down into just a few categories, and maybe the top 15 classes that you want to use. Paper UI construction, pen and ink data capture, recognition classes, doing handwriting and gesture recognition, integrating with graphical user interfaces since paper can't do the output, communications with remote devices, and supporting coordinate transformations. We've now seen the core parts of Paper Toolkit. Next, we'll discuss our evaluation. One aspect that distinguishes this work from the prior toolkit research on augmented paper is the depth of the evaluation techniques, and also our subsequent design responses. So in essence, we improved the toolkit after reflecting on each of the results in our study. And in this final section, I'll actually describe the 4 major results from our study and the 4 major design responses, how we improved the toolkit based on those results. So once again, you're familiar with these terms now. I want to evaluate the threshold. And to do this, I deployed the toolkit in an undergraduate HCI class. To inspect the ceiling, I gave the toolkit to myself. I used it. I also provided it to other research labs, and students in our lab were able to use the toolkit to create new interactions. So let's take a look at that threshold down there. I introduced the toolkit to Java programmers, 69 students in the introductory HCI course at UC Berkeley. The 17 teams used it for 6 weeks to create paper applications, working applications. And all of these students were actually novices to creating augmented paper. And many of them were actually novices to creating graphical user interfaces too, since this was an introductory course. To be clear, I actually provided the core parts of the toolkit to the students without any of the research interactions we were working on at the time. The core included the abstractions for constructing paper UIs, rendering PDFs, handling pen input, displaying ink in Java Swing GUIs on the right, and exporting them to XML and images. So for this class deployment, how do we figure out whether the toolkit is good? What are our metrics? Well, I'd like to examine how usable this architecture is, whether the API is memorable. Can we support a variety of designs? Can these 17 teams create things that span a large part of the design space? And can they actually go beyond what we provided them? Can they hit the ceiling? The data I collected include newsgroup. I supported questions through email. I downloaded and read their project reports. And I grabbed all the source code from each of the 17 projects at the end of the semester. I organized the 17 projects in a grid. You don't have to worry about the details here, such as the interactions they supported, selection, whether they supported drawing interactions, whether the programs were designed for mobile applications or whether they were designed for more than one person. So I'm just going to talk about 6 of the applications here. So the 6. The first one is location-based search. This supports a selection type of operation. A user can go out with a paper map, draw a circle, and say, give me all the ATMs that are nearby. The result is sent as a text message to your mobile phone. Synchronized paper and web planners. A user can cross out a to-do on a paper planner, and this will eliminate the task from your web calendar. Automated ballots. A voter can walk into a booth, tap or check next to the people he wants to vote for. The votes are tallied automatically, but this provides a paper backup. Paper web design supports drawing types of interactions. The user sketches out the website and creates links. These are updated immediately and displayed in a design environment. Paper-based blogging. Entries are written throughout the day and uploaded at night. The project recognized boxes to allow quick import of photographs into those regions. This is inspired by our bracket gesture in ButterflyNet. And finally, music composition. The user just writes music on staff paper, and the computer automatically translates this into a MIDI sound file. As you can see, the projects covered a wide part of the space. As the students didn't have access to our wide format printer, it did cost $5,000 after all, or projectors, they could not build these gigaprints types of applications or ones that supported overlay of digital graphics. At this point, I'd like to talk about how students went about building and debugging their applications. Ideally, the workflow looks somewhat like this. The programmer writes some code, designs the interaction, codes a little bit, tests the application, and hopefully everything works. I can just give the application to the end user. So for all you computer programmers in here, this is not how it happens in real life. As we know in practice, many times the developer creates code iteratively. He might find a bug, he has to locate and fix it. Then he might code some more, test some more, and this might take a lot of time. to understand how we might improve this workflow for our end users, which are the developers, I dug a little bit deeper. I looked into the source code of each project. In total, the 17 projects comprised 50,000 lines of code, 35,000 source statements. And if we can understand this code more deeply, we can actually learn how much Paper Toolkit helped, or whether it helped at all, and how we can improve the workflow, whether there are any opportunities for design. So here are the 17 projects, and I've displayed them in terms of how many lines or how many statements of Java that each project comprised. The blue bars show the statements that actually access the Paper Toolkit directly, calling utility functions or creating new instances of the toolkit classes. And we find that on average, less than 10% of those statements, less than 10% of the total statements, directly depend on the toolkit. So what are these people doing, though, with those 176 statements? If we look a little bit deeper, we can actually plot which classes were used. Just look on the left here. The most used classes are for constructing paper UIs. You have to write code to actually construct paper UIs. This was actually an artifact of me building off of the Swing model, because Swing has you type up paper graphical UIs. So what does this mean? What does this tell us? First, projects didn't require many lines of code to gain benefits from Paper Toolkit. This is good. Second, the lines of code that did access Paper Toolkit, of those lines of code, a large portion actually dealt with constructing paper UIs. Okay, that's not too great, but we can look at that as an opportunity. You know, how can we make this better? So let's turn that into an opportunity for design. All right, so this is the observation. Currently, students have to write too much code. This is not a new result, because in 1992, Myers and Rawson actually found that 50% of code in applications support the user interface. So if we can actually minimize the amount of code that people have to write or edit, so even if you have a GUI builder, you might have to edit that code, we can lower the threshold for the students. We can make it easier for them. So to do this, I'm going to leverage the design practice of sketching interfaces before coding them up. I can actually translate sketches, digitize them, turn them into an XML specification of the user interface. So here we've recognized the sheet. So you just draw a big box of the sheet. We can recognize the regions. We can recognize the handlers that are attached to each region. And the labels that you write next to those handlers are recognized by our handwriting recognizer and mapped to the underlying implementing class. So basically, you can just sketch that and create the user interface. How does this impact or change the workflow? Well, it reduces the amount of code you need to write. So it tightens up that loop just a little bit. It reduces the amount of code right there. And on the learning curve, well, it softens the curve just a little bit. Because whereas we used to have to code to make those UIs, now we can just sketch them. You don't need that extra expertise to create a basic paper user interface. The second observation we made was how developers debugged their interfaces. So this graph depicts print statements. So we noticed that students inserted a lot of print statements to have to track whether event handlers fired or whether parts of their code were reached. So here I show the number of print statements I found in the code and also the values that were printed. The second blue bar there shows that there are a huge number of got here print statements. So these print statements don't actually provide any information other than the fact that the code, the computer, has reached a certain point in the code. So here are some of the examples of those got here statements. System.out.println, we get here, yo, hello. This is on the map region. So in short, students need support for tracking event flow throughout their application. They inserted a lot of those print statements into the event handlers. Right? They didn't know what was happening when they worked on a part of their paper UI. So how do we make that better? How do we help them track event flow? We do this through monitoring. From my observations, I noticed that many programmers use two screens. The primary display houses the source code and the development environment, so I'm coding here. On the secondary screen, usually a developer will place web documentation, console output to help debug the application. Can we actually make better use of this second screen, or can we make additional use of it? So I designed and implemented a monitoring application to sit on top of this toolkit. This application helps a programmer visualize what's going on, especially when his program isn't working correctly. This is the first version. When the user works with this paper UI, an on-screen view shows which regions are currently active. So you don't need those print line statements to say, yo, I got here anymore. This will just automatically tell you that we're getting input. However, this version has a drawback. Every time a developer starts working on a second region, the first one fades away. You lose history, you forget what you were doing. To provide this history then, we present a timeline. So this is the current version of the monitoring tool. On the left, the tool displays what the toolkit thinks your paper UI looks like. In this case, there's a single sheet, 3 regions, and 1 handler attached to each region. As the user provides input to the system, the visual timeline actually tracks all of the events that are fired. So it tells you you're interacting with that part of the paper interface. So you're going, okay, it works. Any application output is also captured by the system. The user can then navigate this history to visualize his test session. Additionally, the lower pane presents a textual view of all the interactions, such as browsing, copying code from the web, searching for code. So let's see this monitoring view in action. Once again, the user provides some input. The system says, I fired this handler. And the application, when the application provides output, it's actually logged so the user can review this timeline. The monitoring system actually listens to 3 applications: the paper toolkit, the Firefox browser, and the Eclipse IDE. So it actually can log the whole development process. Anytime you edit a new class in your application, or you search for code on the web, it can track that in the textual timeline. So how does this impact our workflow once again? It helps developers test, debug situations, such as when the wrong feedback is displayed. So we're actually speeding up the testing there and tightening that loop. As we know, as computer programmers in the audience know, developers test iteratively and frequently. So additionally, hardware such as pens and printers might be a limited resource. So we thus want to minimize this overhead to test. To do this, I allow replay of test sessions. So let's see an example here. The developer writes some code to receive input, and he prints out the stroke data just to see that it's correct. However, he eventually wants to write a gesture recognizer. He runs his application, provides some gesture input, and sees that his application is working. It's just printing out some data. Now, he opens up an ink panel to display the ink strokes. Instead of reproducing his pen actions physically, he can just hit replay, and the application will run. Once again, now he can read up on gesture recognition, implement the gesture recognizer, hit replay, and this time his recognizer will actually recognize all of those pen gestures. So this is how replay works. The input device is our software abstraction that normally talks to the hardware pen. When the developer uses it, the input device logs all of the input to a file. When the developer hits replay, the replay manager reads this log file, sends it back to the software abstraction that normally talks to the serial port. The event dispatcher relays the input to the handlers and activates the gesture recognizer as normal. And if there are any gaps in the test session, such as if you went to get a cup of coffee, we'll just compress those gaps so that the test session is efficient. The huge win from replay is that now the developer can actually replicate his test session elsewhere. Let's say he's working with other teammates that don't have digital pens or might not have the printers to make that augmented paper. These multiple developers can then just take his log file, run it, and test their applications without digital pens. The final challenge that we noted was that printing interfaces interrupts the developer's workflow. With a graphical interface, every time you edit an interface and you run the application, the GUI automatically re-renders itself. With a paper interface, you actually have to go print it. So we'd like to avoid or minimize this printing step. Here I'm printing the 14-foot interactive timeline. It took me 4.5 hours. Not fun. So the solution to this was that we allow simulation of the paper UIs. The developer writes some code, picks up a pre-printed notebook, selects a handler he wants to test, draws a box in that handler, and starts working with it. Here I've augmented a magazine, so I can draw on pre-patterned paper, cut it out, add some glue, stick it on a magazine. Quickly I write some code to calculate the elasticity of a bouncing ball. So now I've created an augmented magazine. This facilitates rapid prototyping. I don't need to print out the whole magazine. So how do replay and simulation affect our workflow? They speed up testing significantly, so we can further tighten that development loop. And how do they impact the learning curve? Well, faster testing allows developers to reach that ceiling with much less work. Now, I haven't run a formal evaluation of these new design responses with actual users, but one way to evaluate them is to use the cognitive dimensions framework from Green. So Green et al. Provide 14 different axes you can actually apply to your applications to figure out whether it makes sense or whether it should work. And I'm just going to talk about 5 of them today. For example, the event visualization, the monitoring, exposes toolkit internals to enhance visibility. It helps the developer understand what the toolkit is thinking. However, these visualizations take up a lot of space, but not as terse as textual displays might be. Ink input and the application output are placed side by side so you can actually figure out causality. Like this event handler triggered that application output. Sketching to create paper UIs minimizes the code you need to write to actually explore an idea. So it avoids premature commitment. You can explore many ideas. Finally, replaying test sessions speeds up testing, so it encourages frequent, iterative testing, allowing progressive evaluation of your application. To summarize the design responses, I'd like to say that we found that people had to write too much code to create their paper UI, so we provide sketching. We found that students had trouble tracking event flow, so we provide monitoring. We found that students, the developers, met challenges with distributed testing. They actually only had 1 pen, and they were a team of 4 at that time. So we provide replay. Printing interrupts the workflow, so we allow developers to simulate the paper UI. And I'd like to highlight once again that the depth of this evaluation and inclusion of design responses is part of what distinguishes this work from prior augmented toolkits, augmented paper toolkits. As you can see, by providing sketching, we lower the threshold, simulation and replay increase efficiency of the developer, and monitoring supports visibility and awareness. How do these design responses relate to previous work? Well, Sketching and simulation extends Landay's work in allowing users to create graphical user interfaces by just drawing them on a digitizing tablet. However, our solution is more scalable because you can actually write the names of the handlers. So as you add new handlers to the system, you can just add new mappings from the new names to the underlying class. Monitoring and replay were inspired by Co's Y-line. For example, here, you can ask a question, and it'll tell you which variables the application has modified. And we don't actually use this directed graph. Our solution is more of a passive solution. It just monitors everything and displays it. We don't ask the user to ask questions. The omniscient debugger uses a more textual display. It also allows saving and replaying of debugging sessions. But the visualizations there are in text. It's more terse, but possibly less understandable to the user. And each of these techniques is not just for paper UIs. We can apply sketching, replaying, and monitoring for creating graphical user interfaces as well. So I'm going to move into the last part of my talk. We've seen how novices use the toolkit and how we responded to the study results. Now let's quickly see what the experts did. To explore the ceiling of the toolkit, I used the paper toolkit. I built gigaprints. Actually, the 3 that we evaluated were built using paper toolkit, the first version. And I didn't have to worry about laying out PostScript or dealing with pen coordinates or passing messages explicitly over sockets. I gave it to research assistants in our lab, and asked them to integrate paper with digital tables, such as the Microsoft Surface that you see. One student created an application that sends annotations from Post-its onto a digital map displayed on that table. A second student allowed users to rotate and zoom digital graphics on the table by placing a pivot with a pen and manipulating the other end of the photograph with his hand. And 2 students created a collaborative design environment. Here, you can draw on paper, send your drawing onto the digital table. The second designer can actually place it onto his sheet of paper. All edits are mirrored at both locations. And finally, the designers can print out their artifacts. So these research assistants covered a wide part of the design space. In particular, they exercised the overlay of digital graphics on top of the paper. Paper Toolkit's open source, like I said. It's been deployed at multiple labs around the world. In particular, the In Situ lab in Paris is using Paper Toolkit to create a butterfly net-like application to support their laboratory biologists at the Institut Pasteur. So what limitations did we find? No toolkit is without its limitations, right? So first, we distinguish multiple users by their pens. That's all we know about. So if a user swaps pens with another user, we can't actually figure out the difference. We only handle output to the remote devices. We don't have handlers to do input from those devices. I don't model erasing. It's a pen. Or undoing. We don't have abstractions to help developers handle incomplete input. So with a graphical interface, you can actually just place constraints. You can gray out the button if a person's not supposed to click it. But with paper, you can't actually prevent a person from flipping to the next page and working on part of the form if he hasn't filled in the first page, right? That's a hard problem. Paper displays cannot currently be updated. So it'd be nice if we presented a way to schedule updates so that the paper display is not just an input surface like we treated today. It might be an output surface that can refresh every day. The main successes are that we presented a low threshold such that students in 6 weeks could create very interesting applications, and a high ceiling such that people in my lab were able to create novel research. And each of those 3 applications you've seen have been published at UBComp and WIST as research posters. extends the GUI model. We evaluate it through source code analysis and present design responses. To conclude this talk, let's revisit our original research questions. What interactions are possible? Which ones are useful? How do we build and test these interactions? How do we test the toolkit itself? Well, here are the answers to those questions. Tools like ButterflyNet provide mobile interactions to integrate multiple types of media. These interactions are great for field scientists, anthropologists, biologists. We found that the ensemble of digital pen, notebook, and camera improves current capture practices. And users found that automatic capture and correlation was a huge win. Tools like Gigaprints provide better visual context and support for collaboration around walls and tables. These interactions are great for teams working with high-resolution information graphics. To support these large prints, we can just use multiple pens, and we combine it with projectors to overlay graphics on top of the paper to simulate future interfaces, like that network monitoring application that you saw. And to build these types of applications, we can use the techniques we developed in Paper Toolkit. It provides a learnable, efficient, and effective way to produce and debug these applications. We treat paper as another input surface without any real-time updates. It provides a familiar starting point to help bootstrap existing GUI developers. By addressing those differences, by routing output to devices or dispatching batched input as events, we can actually introduce these techniques and then depart from the existing model so that the developers can actually create these new types of applications. So we evaluated the toolkit through source code analysis and introduced new techniques to increase the efficiency and lower the threshold for developers. So we see that we've successfully integrated paper into the ensemble of devices. Paper is just an input surface. We've extended the event-based model of graphical interfaces. And we provide a smooth transition to this new world program. In the future, we'll be using tools that are hybrids of today's digital paper, tablet computing, and electronic ink. These interfaces will be large, yet portable. They'll be high resolution, yet very inexpensive. And ideally, they won't take or require any power out in the field. And the insights and the techniques that I've demonstrated today will enable us to create effective solutions now and explore the interactions of that future world. Thank you very much. I'll now take questions. Yes?
So last year at CHI, there was a really interesting talk about environmental sustainability, about how HCI researchers should, part of the analysis of their project should not just be usability, but the impact it would have. And I was wondering if you've done any analysis like that for your project, like for example, the scenario with the gigaprints where they would print down the wall every day. I actually have no idea like what the trade-off is in terms of the ecological impact of throwing away large amounts of paper versus running your monitor longer. So how does the use of paper compare to the use of display power?
Right. So the question was basically, how does using paper interfaces impact the environment, et cetera, especially since there are all these biologists here in the audience. I'm guilty. I've printed out and thrown away, hopefully recycled, a lot of paper in my time. But the gigaprint interactions are actually just, essentially they're prototypes of future interactions. So ideally in the future, we'll have a surface that can just update and have graphical output. But right now, we just actually print on paper to simulate that future interface. So I haven't actually done the analysis to compare whether leaving my computer on all the time, which I do, versus printing many sheets of paper, which one is worse. but hopefully, yeah. Basically, I don't feel that gigaprints themselves, like refreshing them every day, that's not a good idea, right? But that is essentially a simulation of this future type of interface. Yes.
So, do biologists never want to erase anything? Do they typically use pens in the field as opposed to pencils?
Right. I've seen biologists. So the question is, do biologists erase anything? I have seen pencils, but many times biologists will just cross out what's going on. Especially for laboratory biologists that I've talked to who work with chemicals, it's a patent issue. Everything that you invent, you have to write down. If you uninvent something or don't care about it, you cross it out. You never ever just erase anything. So pens are okay because you just cross it out.
Well, it seems like if you had a pencil which had a camera at both ends, so
Right.
it could record pencil notes and you could erase stuff without it being permanently lost.
Right. That's a great idea. You should probably have an eraser with a camera. Any other questions? Yes?
So your major test case was with relatively, in a university sense, naive or beginning programmers. Did you consider, or how do you think it would go with a user population that's, say, domain expert with respect to paper design, form design, for example?
Right.
And is it different with respect to the programmatic aspects? Thinking of sort of the guys that do IRS forms, the
Right.
population, or the guys that do pop-up books, like that. Just,
Right.
How might these observations go?
Right, that's a good question. So the question was basically, I targeted novice programmers, or novices to paper design at least, and did I talk to or work with people who are more experts on paper interfaces? So in short, no, I didn't work with those expert paper interface designers, but many of Anodo's current applications are actually targeted towards those types of domains. Most of the applications are forms-based and do handwriting recognition with paper backup. What we were trying to accomplish here was basically more of a treating paper as a command interface. You might create gestures or use it more fluidly than just entering numbers and words onto a form. So no, I didn't target the experts in paper interface design. But how it might be different is I think those experts might appreciate the Anodo model more than the model I'm presenting in the paper toolkit, because programmers of GUIs, well, they're familiar with GUIs already, but if you're a programmer or if you're a designer of a form, you'd like to think about it as pages and ink on those pages. So that's what Anodo provides now. Yes, please.
It occurs to me that I'm wondering if you looked at this when a field biologist is putting information in a notebook, they go back, they look at that notebook, they enter that information in the computer. That's a really typical process. And in that process, a lot of times you identify errors or problems in doing that.
Right.
Now, if you eliminate the process, do you have any sense as to whether that introduces a new kind of error or problem in that process?
Right. That's a good point. So the question is whether having these augmented tools can actually introduce different types of errors, because if you automatically transcribe people's notes, you might not know that there are 10 errors or 15 errors. So first, one way to do it is to provide some sort of data lineage so you know what happened to the ink, like where it came from, what types of algorithms were applied on it. So we can tell biologists that handwriting recognition was applied to it and it's only 95% correct, then maybe you might want to go through and visually inspect those numbers. So to augment that transcription aid that I presented early in the talk, we can actually automatically do handwriting recognition and then help people do that inspection. So instead of actually automatically transcribing and just forgetting about it, because there will be errors. Any other questions? Okay, if there, yes?
Sure. Design space ontologies are really interesting things, and you've put the design space that you've developed for this area to some considerable work here, using it for evaluation of the projects in Berkeley and so forth. Could you say a little bit more about the kind of development of the design space for this, and whether it certainly was adequate to the task? The question is, do you see it evolving?
Right.
Because how do you know you're done?
Right.
Presumably there are other dimensions that aren't represented there, ones you considered but didn't think of as important as others.
Right.
So it's really a question about the evolution of design space in a way that might articulate the future trajectory for this work.
Right. So the question is basically, how did we design the design space, and how might it evolve in the future? So there are actually a number of other axes I didn't display on that design space. One way to think about it is just what types of interactions you have between the paper and the digital world. Right? So one design space is basically selection, transporting, associating media, or manipulating media. So those are 4 of the axes I didn't display today. And this design space was actually constructed based on a couple of prior design spaces. The first one was from Foley and Wallace in 1974, how they talk about selection and picking with a mouse in a graphical interface. And we looked at that to say, oh, okay, we can apply that to the pen and say we can select and we can use it to choose values. So we also built off of Grimbertier's design space in 2003, and actually Scott Clemmer's design space in 2004, talking about how digital graphics can be either overlaid on top of the paper or presented side by side, co-located, or sent to a remote display. For example, the blog interaction has remote feedback. It's uploaded to a website. So I build off those types of those previous design spaces, and hopefully, I don't think it's done. Someone else will improve upon it. Yes?
Yeah, I love your paper toolkit framework. I assume that you released it open source, and I was wondering if when that happens, sometimes people take the open source toolkit and they go, maybe I like to do it this way. Have you seen any evolution of your toolkit, like Paper Toolkit Plus or something targeted towards gamers?
That's a great question. So it is open source, but there's one limitation. This toolkit depends on hardware, right? So it's not as easily pick-upable by other developers out in the field. So there haven't been many other developers that have created an offshoot from Paper Toolkit. However, people have downloaded the toolkit and are using it. So those who work in research labs who have bought Enodo pens and also have bought the Enodo SDK, which the toolkit builds on top of. So, okay, I'd like to take a few minutes, just 1 or 2, to acknowledge some folks that have helped this process. My committee. Roy P. is the chair of my committee. I actually met him very recently, but he's a super sharp guy. He actually was able to give me great feedback on my work. He was like, oh, so what's the delta from prior work? I figured that out. Manish supported the deployment to the UC Berkeley class. He taught that class that semester. Andreas introduced me to this world of field biology. Gave me essentially my first research grant that I was able to work on. Terry was my first advisor here. I joined the HCI group because of Terry. He was a really friendly guy. Of all the professors I talked to, I was like, oh, I can chat with this guy a lot. And actually, the students in his lab were really friendly too. I think it's the human computer. Scott is a great advisor. The nice thing about Scott is he just trusts his students to get the job done and to do it the right way. So I thank you for that. And another thing about Scott is that I will never, ever, ever beat him down the slope on a snowboard. So I give up. Collaborators. Joel Brandt, where are you? Oh, you're not here. A lot of this work couldn't have been done without Joel. He helped out a lot of the gigaprints, and many of those videos were actually filmed by Joel. Brian, Trinyan, and others also helped out some of my papers. I mentored a bunch of folks, master students and undergraduates. Hopefully, those of you who are around here, well, maybe one of you, hopefully you guys learned as much from me as I've learned from you, because I learned a lot from working with students. People in my lab who watched my talk, the biologists. Rodolfo is actually teaching a class right now. He's a great teacher. He was the person who actually took me down to the rainforest I observed his class, the participants in my studies, National Science Foundation. They gave me money so that I wouldn't be poor and eat ramen all these years, but I do like ramen. Intel, Nokia, and Okio provide some hardware. John, Bert, Heather, and Ada actually helped to run the lab smoothly. And I would never get reimbursed for any of my work if Heather and Ada weren't in the lab. Research is powered by Jing Jing, Baker.com in our lab. I have many friends that have made this experience much more fun. And you all know who you are. We're going to have dinner tonight. And my loved ones. My mom and dad actually made it out today. Thank you. Thank you so much. Sue, thank you. I love you. I can't thank you enough for helping to keep me sane through all these years of being my best friend. And one last story I'm going to tell is my mom and dad in the 5th grade said, if you get straight A's on your next report card, we're going to buy you any video game you want. So of course, I got straight A's, and I got Teenage Mutant Ninja Turtles. And well, I was like, can I do this again? So after getting many video games, they realized it wasn't a great deal for them. They're like, you know, what are video games going to do for you? Well, it introduced me to computers. It got me hooked on computers. And actually, it made me hooked on interactive computer graphics. So thank you.
What's important is that we saw the whole inside. And then you were showing your time. That's pretty good. I seem to have some sort of right.